All right, without further ado, I'd like to introduce WHCCCN from Lakeville, Pennsylvania. Take it away, sir.
Good evening, everybody, and thank you all for checking into the conference. I hope that you'll learn something and enjoy it. My name's Hank, call WA2CCN, first licensed in 1957. I'm an extra class license, the emergency coordinator for Wayne County, Pennsylvania, the district emergency coordinator for Eastern Pennsylvania, District 3, and yeah, a bunch of other ARRL assignments. I'm a retired engineer, electronics and mechanical, and I'm old, I got gray hair, and I'm fat. So in any event, those are important criteria nowadays. But any event, let's get on. We're going to talk about the off-center fed off-center fed dipole antenna. And let me bring that up here now. I want to share the screen, but I don't see my. Okay. Let's see if I can open this up now. What we're going to discuss this evening is, first of all, just to begin the discussion, we're going to talk about some standard dipoles and how they perform above real ground. We're going to take a look at gain, source impedance, and radiation patterns, and how they change as we change the elevation of the antenna. And then we're going to start moving the feed point off to the side and show what happens when we start going into the off-center fed dipole configuration. Obviously, the dipole, standard dipole on the left-hand side is symmetrical. It's got half of the antenna to the right of the feed point and half of it to the left of the point feed point. The antenna is roughly a half a wavelength long, so really it's at the quarter wavelength point that the feed line goes. The off-center fed dipole, in the old days, we used to call it a Wyndham antenna. It's been around forever. They changed the name of it, and all of a sudden everybody thought it was a brand new antenna, but really not. It's been around for a long time, called a Wyndham antenna. Now, the important thing for figuring out how this works is to understand the current and the voltage on a dipole antenna. On a half-wave dipole antenna, the voltage is at a minimum and the current is at a maximum at the center of the antenna. So if you think of Ohm's law, the resistance or the impedance is the voltage divided by the current. So if the voltage is very low and the current is very high, the impedance is going to be low. However, at the end of the antenna, where you have very high voltage divided by very low current, the impedance is going to be very high. So there's you have the reason for a low impedance at the center and a high impedance at the end. Now, when you start operating this with on harmonic frequencies, so instead of having a single sine wave, you have a double sine wave or sometimes 3 or 4 sine waves. There is a magic point out here where the voltage to current ratio is pretty much the same regardless of which band you go on, and that is one of the key points in how a Wyndham or an off-center fed dipole antenna works. Here's basically the same idea here. The voltage is at a minimum in the center and the current is at a maximum. And so your impedance would be very low here, and the impedance goes up as you go towards either end. And of course, depending on which end of the cycle it is, the way the current would flow back and forth in the half-wave dipole antenna. So you just got to keep that in mind as we go on and talk about the rest of the antenna and the how the off-center fed dipole works. Well, it's time to go into easy neck. So let me just launch that. And what I'm going to start off with doing is to create an 80-meter dipole here. And to do that, I'm just going to randomly pick a dipole antenna that's in the file.
Hank, you need to switch share windows because you're still sharing PowerPoint.
Okay. I need to look at my...
Just click share screen again and share the EasyNet screen.
Does that do it?
I've got it.
That's the ticket.
You see the EasyNet in the upper left-hand corner?
Yes, sir.
Okay. So I randomly selected a dipole antenna right here out of the files for the antenna, and we're going to take that and we're just going to modify it. I'm going to start off by changing the frequency to 3.5 megahertz, the low end of the 80-meter band. And then we got to make sure that we have a ground that's a real ground. And let's make sure that our units are in feet so that we can understand what that's all about. Okay, so let's talk about the wires. And I'm going to make the wire to start with, let's say 135 feet. And I'm going to put it, now this is interesting. Everybody says that for an antenna to work good, it should be a half wavelength above ground. Well, for 80 meters, half wavelength would be 40 meters, which is roughly 130, 140 feet. So just for the heck of it, I'm going to put the antenna at an elevation of 150 feet. Not too many of us can put an antenna, horizontal antenna up 150 feet, but we'll start there so you can see what happens when we start changing the elevation. Let's see, there's going to be at 0 feet here and 135 feet here. And the antenna is going to be 150 feet high. Okay, and now let's take a look at the antenna. All right, that's what the antenna looks like. Right now, we're saying that it's an elevation of 150 feet, and the antenna is 135 feet long, and the feed point, the source, is at 50% of the total length, 50% from the end. So there is our typical dipole antenna. And let's see where the SWR is. We're going to start off, because I have no idea, I just randomly threw a number up there. Let's do a sweep from 3 to 5 megahertz. And we're going to sweep it every 20 kc. And it may take a while to run the calculations. There we go. All right, there's our antenna. And we have over at this point here, it's at 3.58 megahertz, pretty close to the low end of the band. And SWR of 1.22 to 1, because the impedance of the antenna at that point is around 61 ohms. So that was a good number to pull out of my hat, 135 feet. How did I know that? Because I did this before. So let's go back here to the chart and redo the SWR from 3.5 to 4. And we'll do it every 10 kc. And we'll get a better picture of what the antenna looks like. Okay, there we are. And that's good for the antenna. Now, what does this antenna look like in terms of its radiation pattern and everything else? Well, let's take a look at the plot and see, pick an elevation angle of, 45 degrees. And we'll look at the azimuth. So at 45 degrees, we start to see the characteristics of the dipole antenna here, where off of the broad side to it, it's got the maximum gain, and off of the ends, it's down around 5.5 dB. And the outer ring here is 4.11 dBi, which is roughly 2 dB of actual gain. So let's take a look at the elevation chart. Okay, here we go. Now, at 45 degrees, you see the gain here, the maximum gain of the antenna is actually around 8 dBi. But at the 45 degree angle, I was down 1, 2, 3, 4 dB. So that's where we got it from before. So I come over here, see where the maximum gain is at, roughly 5, 10, 15, 20, 25, 26 degrees. So if I come over here, change the angle, the elevation angle, not the azimuth, not the azimuth angle. Plot type azimuth angle to 25 degrees, say. And we do the azimuth plot again. Oh, didn't pick up the angle. Don't know why. There we go. All right, now you can see the 8 dB that we saw on the other chart, and you still got even more of a figure 8 pattern of a typical dipole. You got 8 dB off the broadside, and you're down 11 dB off of the ends. So what does this look like in 3 dimensions? We can do that too. This kind of looks cool. And you can see that this antenna would be pretty good for DX because it's got a pretty low angle of radiation, 25 degrees. But you also got a little bit of a hump in the middle here, so the NVIS wouldn't be too bad in terms of local contacts. So what happens if we bring the antenna down? Whoops. It's already running. What the hell? That's what happens when you push the wrong stupid. Now, where am I? It says it's already running. That's not what I wanted to do. I want to run that. That's what I want to run. Okay. Lee, can you see that okay? I just don't have the yellow in the background. Can you see it okay?
You're not sharing the screen anymore. You got to reshare.
Okay. Okay, can you see it now?
Yeah, you've selected only one window. We're not going to get everything. You got to share your desktop. I would recommend you just hit share screen again and choose screen 1, and that'll show your main desktop and everything that's on it. This way you can switch app we'll see whatever you're doing.
All right, now screen one, stop the share.
You don't have to do, well, you can stop the share, but just hit share screen and share the top left choice, and that'll give me everything on your desktop.
You see everything now?
Perfect. Thank you.
Okay. Sorry about that, guys. Anyway, the bottom line is you can see what this antenna is doing. Now what I want to do is I want to come over here, and with my wires, I'm going to bring the antenna down from 150 feet to 50 feet. And we'll see what that does to the pattern. Okay, first of all, let's run the SWR. Voila, when we lowered the antenna, we increased the capacitance between the antenna and the ground, which has a tendency of lowering the frequency because of the capacitive loading. So my 135 feet is no longer good. So I'm going to have to come in here and change the length of the antenna from the 135 feet to, I don't know, 130, let's say. That may be too much. Let's say 132. Run the SWR again. Okay, so now we're back here, and we've got a 1.12 to 1 SWR. And you can see what happens at the high end of the band, the 4 megacycles, high end of the band here. It goes way above 10 to 1 SWR. That's because the 80 meter band, 75, 80 meter band is so wide compared to the frequency. But in any event, we now have the thing resonating again. So let's go back here and take a look at our plot and see what our plot looks like. We'll use the Azimuth again. And we'll leave the 25 degrees in there and see what it looks like. Well, this is what the pattern looks like, pretty much the same. But notice the gain, the outer ring has come way, way down. Okay, that's about unity gain, dBd, at 50 feet. So we lost some gain when we lowered the antenna. But let's see what happened to the elevation angle. It's no longer going to shoot the signals out to the side. Now we have an NVIS antenna where the signal is shooting pretty much straight up. And you'll notice that the outer ring is 7.4 dB. So we were looking at 25, 5, 10, 15, 20, 25. We were looking at the gain at an angle of 25 degrees, which was down 5 dB from what it was up here. So if I come over here and change the elevation angle to 90 degrees, looking straight up, look at the plot again, you can see we have our 7.14 dB gain shooting straight up. So this makes a terrific antenna for close-in work up to around 300 or 400 miles, even at only 50 feet. And the SWR is still pretty good. We ran the SWR and just look at it again. You can see that it's almost 50 ohms at this point, 62 ohms or so forth right down, right, at 56 ohms. So it's excellent. So what happens now if we bring the antenna down even lower? Instead of 50 feet, let's bring it down to 25 feet. Now, a lot of people have their 80 meter antennas, long wire antennas at 25 feet. This is not an uncommon situation. So we have to run the SWR again, see what happened to that. Oh boy, the SWR went way up. And that's because the impedance, let's see here, the impedance is here, is way down at 18 ohms. That's why the SWR went up. So the effect of lowering the antenna real low is lowering the impedance. So if you have a dipole that's that low, the smart thing to do would be to use a 1-to-4 balun. And I'm going to show you how that would work. A 1-to-4 balun would take 12.5 ohms and make it 50 ohms. So if you take this antenna here and use a 1-to-4 balun, you can get a pretty darn good SWR down at the lower overall heights of the antenna. However, you notice the bandwidth of the antenna has also sacrificed. So these are the effects of raising or lowering the antenna above ground. And of course, I'm using an extreme situation, an 80-meter antenna. You go higher in frequency, it's not that hard to get the antenna a half a wavelength above ground. But that'll give you a good idea as to what we're doing. So what I'm going to do now is I'm going to go back to 50 foot for the antenna. All right, and we'll just run our SWR again just to make sure we're back to where we were. And 50 ohms, okay. Much broader frequency coverage, and we got a low SWR down here. Okay, now let's see what happens when we do an SWR plot from 3.5 megacycles up to 30 megacycles. And I'm only going to do this in 50 kc steps because it would take forever to run the calculations. So let's run the plot and see what it looks like. Okay, here's the 80-meter antenna. And since it is center fed, the only thing you're going to see is the odd harmonics. You're not going to see the even harmonics. So here's 3.5 where we started. And 3 times 3.5 would be 7, would be 10.5 megacycles. And over here, 11 megacycles. I'm a little bit above 3.5, so it's 11 megacycles. That's your third harmonic. And this is your fifth harmonic at 18 megahertz, and your seventh harmonic up at 26 megahertz. So you can see the odd harmonics of the antenna, and that's all you're going to get. So that's where the Wyndham antenna comes in. So now what we're going to do is we're going to take the wire, the source, excuse me, and instead of being at 50%, we're going to move the antenna off to maybe 30%. And now we're offset. And if we look at the antenna, you can see that we have come off of the middle and we are now feeding the antenna 30% of the total length over here. So what did this do to our plot, our SWR plot? Wow. Now I'm starting to see all the other harmonics. Before we saw one over here, we saw one over here, which was the 11. We saw one over here, I think this is the 18. And we saw one here, but we're starting to see the second harmonic, which is 40 meters, 7.135 megahertz. Now we're seeing the second harmonic, third, fourth, fifth, sixth, and seventh harmonics. Okay? And these are pretty high impedance. This one is, this point here is 146 ohms. This point here is 2,700 ohms. This one here is 194 and 150. So the impedance has gone up because we have moved further out So we now have a higher voltage and a lower current. So the impedance starts to go up. So let's take our alternate impedance here. And instead of being a 1-to-4 balun, let's make it a 4-to-1 balun, which takes your 50 ohms up to 200 ohms. So now watch happens when we change the impedance of the antenna to 200 ohms. Wow. Now we've got really low SWR here on 40 meters at 1.41. 20 meters, practically perfect SWR. 18 is pretty low SWR. 15 meters is now starting to get realistic. The SWR is still high because the impedance is still much higher. And we're up here on a 10-meter band. Okay. So that's what happens when we went to 30% off. Well, let's see what happens if we make it 20%. And we'll run our SWR again. A lot of calculations taking place every 50 kc. Oh, wow. Now we got 40, 20. See that this is 40 here. This is the third harmonic. Here's 20 meters, 18, and here's 15 meters. So in the last one, we had a low SWR on 20 meters, but a high SWR on 15 meters. The point being that you can play with these, with the position of it to pick up 20 meters or 15 meters. And that way you can optimize the position of the tap depending on the band that you want to go at. Another alternative would be to use a 6-to-1 balun instead of a 4-to-1 balun. And if we did that, that would be 300 ohms here. And that helps smooth things out as well. So by virtue of using a proper balun transformer, probably a 6-to-1, optimizing the point of the tap somewhere between 20 and 30 points, you can get the old conventional dipole to work on multiple bands. And that's basically how a Wyndham antenna goes. So Lee, why don't we throw the mics open and see if anybody has any questions?
All they have to do is unmute, sir.
Anybody has a question, just unmute yourself.
Good job, guys.
Thank you. John, what do you think there? K5 VGM. You got to unmute your mic. You got to unmute your mic. John, K5 VGM, unmute your mic. Lee?
John, unmute yourself. John Parmalee. You should be able to unmute yourself.
You'll be looking at a lower left-hand corner to unmute yourself.
Yeah, everybody can unmute themselves. I've got it enabled. I've got it enabled. I'm going to ask John to unmute. Okay, Mike, I see Pete Marcano can unmute. Herb is unmuted. KB3ZW is unmuted. Chip's unmuted. So everybody's able to unmute themselves except for you, John.
Got your computer, you can hit the space bar and it usually unmutes you as well.
Yeah, you can focus the Zoom meeting window and hit the space.
I have a question.
Hank,
Yeah,
this
go ahead.
is Keith, AM5G. He's the CW maniac up here. He's down the road from me.
Diddly da da.
Yeah, diddly da da. Yeah, I'm ambassador for the CW ops here. Anyway, I've got a 160. I've got a 160 OCF. Sound like several of us talking. Anyway, I have a 160 through 6 meter off center fed dipole. It's a what's that one that can't remember, Buckmaster. And I run all the bands. 15 meters is pretty high SWR. I wondered if I got it higher.
Well, the impedance at 15 meters on on this kind of an antenna, on a Wyndham antenna, is not only a function of where the tap is, but it's also a function of the elevation of the antenna.
Do you
So,
think if I got it higher, would it be better?
yeah.
Okay, right now it's about 60 feet, but I can go to 150 if I need to.
Right. The higher the antenna is, the more it begins to replicate a free space antenna where you would get the resonances, constant impedance resonances on all harmonics.
Okay.
Keith, how high are you at the ends?
Right now I'm at 60 feet.
Is that a flat top?
Not quite.
But pretty close, okay.
But if I go to 150, it will not be a flat top. It'll be more of an inverted V.
Yeah. By the way, inverted V antennas work terrific. They still retain the NVIS characteristics, but they also bring out lobes that start shooting off to the side, so they're better for greater distance as well. And the other point is, on each one of these harmonics, you will find that they have much different characteristics as far as the radiation pattern is concerned. We only talked about the radiation pattern down at 3.5 megacycles, but if I were to look at the radiation pattern on 14, say 14, man, 14, do that.
Anyway, I appreciate your presentation.
AK5DO, Bruce and Roman Forest, ready with training and your backup.
Yeah.
Hey, Keith, we could take a couple shots at the top of your tower with my air cannon and see if we can thread it and get a rope through it there.
See, this is what happens to the pattern of that antenna at on 20 meters. See, it's no longer just shooting straight up. You're starting to get lobes of the pattern off to the sides, which would
Show
be
us what
great.
happens to it in the azimuth.
Yeah, let me show that. Let me show you that in with the this ought to really look pretty.
I think you
start
could
getting
tag that.
signals off the end of the antenna and off of the top of the antenna and everything else as you go up. I mean, the radiation pattern changes dramatically on each band.
Can you spin it down to see the NVIS?
Oh crap!
Just minimize your browser there for a second. Your Google. Just on the right side, just hit the minus. No, not that. The window behind it.
Love it.
This.
Oh no, above it. Post to 10D zoom. Your web browser. Just minimize that window. Up, up, up. Move your mouse up. Mouse up, Hank. Up.
Little up higher.
Where?
No,
New
man.
share?
No, move your mouse up until I say stop. Move your mouse up, Hank.
It's all the way up at the top of the screen.
Oh, okay. Well, I don't know why, but your web browser's blind. Anyway, the dipole in free space, the 3D diagram. Can you
This one?
spin? Yeah. Can you spin that so we can see the Z? In other words, bring the lobe closest to you down so we can see it more of a top view. Can you do that? There you go. That's what I was looking.
There you go.
Yeah, I want to see how high the Z is for NVIS. Oh my goodness. It looks like the Epcot Center
Still pretty
World.
good. But notice you're getting some signal off the ends of the antenna as well as broadside.
Yes.
Every place that you have a null, you make up for it with a lobe, and those lobes are stronger because of the energy that was sucked out of the null.
That's right. That's exactly right. So you do have gain there.
Hank, Chris, W5HLO has a question. Go
Yeah.
ahead, Chris.
Hey, thanks, guys. And thanks for letting us come in. I'm actually down here in Houston, and we got word from the local areas coordinator that y'all were doing this. I appreciate you having us. I was wondering if you're going to do an inverted V, would you recommend having the feed point at the peak, or can you put the peak somewhere on the middle of the long wire, or does it matter?
The highest current point is where you want the antenna to be. So on an off-center fed antenna, you would still try to put the peak where the antenna is and feed it off center. But put the center of the antenna as high as you can, because that will always be the highest current point.
Okay, so since the center of the antenna would be part of on the long wire on the 60% or the 70% wire, you'd have the feed point offset from the center.
Yeah, a lot of people do that because the balance transformer is heavy, and you really don't like to have a balance transformer unsupported, just supported by the wires. So the truth of the matter is, from a theoretical standpoint, you want the center of the antenna as high as possible. From a practical standpoint, you're not sacrificing very much by putting the balun at the highest point.
Okay, thanks.
All right. Any other questions?
If you have a question, I muted everybody again. Just either raise your hand or unmute yourself and let yourself be known.
I have a dumb question.
Go
All
ahead.
right, Pete, KC3POC, go with your question.
All right. I'm getting ready to put up an off-center dipole antenna. Do the ends of that have to be 100% diametrically opposed, or can they be in a V-ish formation?
Well, the antenna will resonate if it's not straight across, but it's bent, and it'll still work. That will affect the radiation pattern of it, and it probably will have a little effect on which harmonic is better. I don't know. I haven't modeled that.
It's going to move your lobes around some. You'll pick up some new lobes and lose some.
Exactly. Yeah. Yeah. But it may affect the impedance as well.
Well, if you fold it all the way around, you got an in-fed folded dipole.
Well, yeah, that's correct. Or if it folded all the way around, you could have a loop.
Yes. That's what do you think would happen to Keith if he were to take that 150-foot tower and make a sloper out of it?
Yep. Now I'm going to show you now the 75, 80 meter antenna that I designed.
Hank, before you do that, you got a question from KB3ZW. John.
Go ahead, John.
Thank you very much. Hank, I just in your charts, you neglected to let us know what gauge wire you use. How that, if you went to, let's, for instance, you used 14 gauge wire and you went to 10 gauge wire, would also increase your bandwidth. How would it affect the SWR on multiple harmonics?
It wouldn't have any effect at all. This antenna we just did here is modeled on 16 gauge. If you were to increase the diameter of the wire to 14 gauge or 12 gauge, the only effect that it would have would be the length of the antenna would be a touch shorter to get to resonance. But in terms of the ratio, where you put the tap and where the feed point and so forth, it wouldn't make any difference.
Okay, thank you, Hank.
All right, Hank, we've got a question from George, N5 NBS. He found
Go
a
ahead, George.
design for a 5/8 slope folded dipole terminated. It fits his backyard width, which is 85 feet. He's not sure how much height he can support, and he'd like your opinion.
85 feet.
His question is in chat, unless he would like to unmute himself and say it verbally, George.
Well, no, just repeat it to me again. I'm getting some squeaking there from
George,
other mics.
you need to unmute yourself, George. Okay, until he finds the, there he is. And we're not getting audio. He found a design for a 5/8 sloped folded dipole terminated. It fits his backyard, which is 85 feet wide. Not sure how much height he can support. What are your suggestions?
It's a 5/8 wavelength antenna instead of 4/8.
George, your audio is not coming through. Your audio is not coming through. George, just nod your head. Yes, it's 5/8.
I don't know. I think that that would 5/8 wave antenna is going to be beneficial for the harmonics. I don't think it's going to do anything for your fundamental.
My suggestion is get a copy of this program, learn a little bit about it, and then put 5/8 wave into it and play with it.
Yeah.
You'll learn a whole lot about how antennas work if you can master a modeling program.
Any other questions before I move on?
Next question comes from Keith, KC3NDU, who's also Mel, KC3NDW.
Go
Hey,
ahead,
Hank.
Pete.
How are you, Hank? Great presentation. I have a question for you. With say you have a Buckmaster, can you hang that off of a tower? How does would that interact with the steel, or do you need to have it mounted off of something that's not ferrous?
It works fine hanging off of the steel tower.
All right.
I don't
good.
care if it's the end of the tower or the center of it. It's not going to make any difference.
I can second that because I've got a Buckmaster off of my 100-foot tower and a second one held up by nothing in the middle of my yard, just held up by the wires on each end, and they work fine.
Great.
Okay. I'm going to throw up here now the antenna that I was talking about earlier, my 75 to 80 meter 2-element half log cell antenna. See if I can find it here. Okay, now this is what the antenna looks like. Let me see if I can zoom in on that a little bit. You'll notice that the feed point is in the center of this 10-foot section here. So the way that this works, it's a log cell. So the longer wire from here across here and out to here provides a lower frequency resonance, and the short length from here across the center and out to here provides a higher frequency resonance. And the way that this looks, if I run the SWR from 3.5 to 4 in 5 kc segments, now that's across the whole band from 3.5 to 4 megahertz. The SWR is around 2-to-1 all the way across the band. And at this point, it's lower than 50 ohms, 36 ohms, 37 ohms. At this point here, it's a little higher, 65 ohms instead of 50 ohms. But you got about a 2-to-1 SWR all the way across the band, which can, a rig can handle that even without an antenna tuner. And all of the antenna tuners that are out there are well within the capability of taking a 2-to-1 SWR down to 1-to-1. I did this model using a flat antenna. If I were to drop the ends into an inverted V configuration, it would have the tendency of lowering the SWR a little bit, so that at no point in the band would it be more than 2-to-1 SWR. John, how do you like that?
That's a pretty good antenna. I'm wondering how far does this extend in the direction of 160 meters and 40 meters?
It works. I've modeled it.
Can you show me a 1.9 to maybe a 7. Or to 8?
Well, this is specifically for 75, 80 meters. This is not an antenna that's going to work on harmonics.
No, yeah, okay. I just wondered what it would look like out of the band.
Yeah, it gets weird.
Okay.
What I have this antenna in an inverted configuration here at my home station, and I have used an antenna analyzer to verify that this SW curve is for real. Up on my tower, I have a rotatable dipole for 40 meters, and that's up about 60 feet. And on top of that, I have 2-meter antennas, 8 elements vertical and 8 elements horizontal. And the base antenna at about 55 feet is an 8-element log periodic that covers 10, 12, 15, 17, and 20 meters. So that's my antenna farm right now. And I've got a butternut vertical in the back for 160 meters. But I've done this modeling on this, built it, it works great. I showed it to a couple people, and at the present time, there are 4 EOCs, Emergency Operations Centers, here in Eastern Pennsylvania that are using this antenna, and found it to be perfectly functional across the band, just like in my home here. In fact, the one that's at Luzerne County, the apex is at 70 feet and the ends are down to about 35 feet in the inverted configuration.
These wires are 10 feet apart?
The one that I have home here is 6 feet apart.
I see. But the trick is that you've got a length of wire that's, you've got a path that's in the high end of the band, another path that's in the low end of the band.
Right. And it zigzags just like a log cell. And the sucker just flat out works.
Let me suggest another broadband antenna is not a doublet, but a 3-wire antenna, where you've got 3 wires parallel shorted at the end, and you feed one in the center, and that'll stretch the band out a lot too.
Not like this.
No, but it will stretch it out. Hanging 2 wires parallel could be a bit of a chore.
I've modeled all kinds of things. I've modeled the bazooka antenna. I've taken antennas and tried to make the elements real wide by using a cage type situation out of them. Nothing comes anywhere close to this.
I'll have to try it.
So any event, that's my magic antenna for, it's interesting to look at the pattern. If I just spread out the SWR here, look at it from 3 to 5. And you can see what's happening. Okay.
Well, that's nice.
And So you're seeing exactly here what would, you know, what your pattern is, because this point right over here is like 3.515, and over here is 3.985. That's the whole band right there.
Yeah. I'm wondering what this thing would do on 440.
Before
I
you
think
do
this-
that, Hank, could you show me what the 3.873 point is? Just to the left of the green dot. Let's see what 3.873 is.
3.873.
That's about right.
388, 1.72 to 1.
That seems like that might be my solution here. Because that's exactly the frequency I'm looking for NTS.
You see, I operate a lot of CW.
Sorry to hear that.
So for me, my Eastern Pennsylvania emergency phone and traffic net is at 3918, which is 3930, right about there. And then down here, I'm in the middle of the CW band, 356, 60 KC up. So it's perfect for the high end of the band for nets and the low end of the band for CW.
But even the middle of the band is acceptable.
Oh yeah, I mean,
There's
anyway,
nothing bad about that antenna.
yeah, it works great. So in any event, that's my magic antenna, and I use this program to develop the antennas that we used on a railroad train. We did a drill up here where we operated from the caboose of a railroad train, and we were allowed to put an antenna on a flat car. However, the antenna had to fit within the profile of the flat car and not be any higher than the caboose, because we were going under trestles and there was trees and everything adjacent to the train tracks. And I used horizontal loops, 2 of them, one inside the other, one loop for 40 meters and one loop for 20 meters. And it was really weird because the flat car was conductor steel, and the antennas were only about 10 feet above the flat car. So there was a tremendous amount of capacitive loading on it. But I used this software to model those antennas, and they worked out great. That was quite a deal operating railroad mobile. So anyway,
How'd you manage that, for God's sake?
yeah. You can do lots of stuff with this thing, and it's after a while it's a lot of fun. Here's one other one that I did. Let's see if I can find it. All right, I have a Surveyor travel trailer, and I put a what the heck? It's an Eagle One vertical antenna on the travel trailer, bolted to the ladder that's on the back of the travel trailer. So I modeled that.
Is that the telescoping one?
Yeah.
A 32 foot?
Let me pull that antenna up again. Open the description. Where the hell? Here it is. Okay. Now that antenna worked terrific on 40 meters and above, but it wouldn't work for dingus on 80 meters. It just wasn't a long enough vertical antenna. So we were talking about all kinds of different ways of adding some wire to the top of the antenna to get the thing to resonate. And finally, I said, why don't I just put a loading coil down at the bottom of it? So here's a view of the, I'm still not on that. I'm still not seeing that. Why am I not seeing that? Open this antenna. It's not coming up.
Heck, I think you saved over it.
Yeah, you saved over it, Hank.
If I may have done that.
Can you kill the existing display?
No, that's that. I think you're right. Yeah, I lost it. No, well. I can pull it up from my other computer, but I did a wrong thing here and saved on top of it. Anyway, that's the deal. Okay, so that's how an off-center fed dipole allows you to work on multiple different bands where a dipole won't. And it really works.
All right, if
Any other
anybody
questions?
has any questions or comments, you can go to the reactions button at the bottom of your screen and raise your hand. John's
Thanks
doing
so
it.
much for the
John's doing it the
presentation.
old-fashioned way.
Go ahead, John.
I just wanted to suggest another whole different approach to a tower. And that would be to take a wire at perhaps a third of the way up the tower, stretch it out as a sloper, just a wire now, and bring it down to the ground, and also bring a conductor from the base to this point where it comes down to the ground, and put a antenna tuner right there at the base of the antenna. They call it a shunt fed antenna. A number of broadcasters use that sort of thing. You won't find 50 ohms at that point. You won't find near 50 ohms at that point. But it does have some good patterns, and it will radiate and give you a little bit of gain, especially on the upper frequencies.
Yeah, slopers have been around for forever, and they are somewhat directional too. I know guys that have used.
I'm not talking about a sloper.
Oh no.
This is a piece of wire attached to the tower that comes straight to the ground, and your feed point is right at the ground.
It's like a vertical with the end of it bent over.
Sort of.
You have to have a good ground for that, though.
No, well, surprisingly, you don't. If you play with it, you basically have a triangle, and then you have an extension above the triangle.
Okay, so you're bringing the end of the antenna back to the tower.
Yes.
Oh, okay.
I worked for a broadcast station where we had a transmitter with a piece of wire coming right out of the top of it, and it went through the roof, went up and grabbed our 200-foot tower at about the 50-foot level, and then of course we had a ground strap back to the transmitter, so you had a loop there.
Yeah, I was just going to say it's a loop antenna.
But you also have that extension of another, in this case, there's probably another 150 feet of tower above it that was part of it.
Okay. Well, antennas can be fun. So it's one of the few things that is really left up to the experimenter. Today you buy a transceiver and bang, you're on the air. What do you got left? Mother Nature likes a lot of wire hanging in the air.
Yeah.
And you just can't beat that with shorter antennas or anything else. And get a lot of wire up in the air. Any other questions?
I'd just like to invite you to our NARS meeting. What's the date? I think it's the 19th of March. John Portune, who manages to have an antenna project almost every other month in QST, will be our guest.
Ah, great.
He's going to talk about a center-fed half-wave 40-meter antenna with shortened ends on it. He's basically putting a coil in the middle.
Well, now you can show him how to make one that'll cover the whole 80-meter band.
Yeah, I'll pass that on to him. Unfortunately, he lives in a mobile home, but he does have, he goes out to Vandenberg Air Base, and I guess they've got all kinds of antenna playground out there.
Yeah. Okay. Anything else? Anybody else? See, we still got a lot of people here.
They haven't run off.
Well, I shot my wad. That's all I got.
All right, I'll make sure and stop that.